Adjacency matrices of graphs. Definition 10.13. Let G be an undirected graph on n labeled vertices, and define an n by n matrix A equals to AG by setting Aij equal to the number of edges between vertices I and J. Then A is called the adjacency matrix of G. Example 10.14. If G is the graph shown in figure 10.7, then AG is equals to 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0. If G is directed, then we can define its adjacency matrix by setting Aij equal to the number of edges from I to J. Thus, the adjacency matrix of a directed graph is not necessarily symmetric, while that of an undirected graph is. Example 10.15. If H is a directed graph shown in figure 10.8, then AH is equals to 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0. The adjacency matrix of a graph comprises almost all properties of that graph. There are several situations when it is actually easier to solve an enumeration problem working with AG than working with G. A basic result in that direction is the following. Theorem 10.16. Let G be a graph on labeled vertices. Let A be its adjacency matrix, and let K be a positive integer. Then Aij to the K is equal to the number of walks from I to J that are of length K. Proof by induction on K. For K equals to 1, the statement is true as a walk of length 1 is an H. Now assume that the statement is true for K and prove it for K plus 1. Let Z be any vertex of G. If there are Biz walks of length K from I to Z, and there are J walks of length 1, in other words, edges from Z to J, then there are Biz times Azj walks of length K plus 1 from I to J, whose next to last vertex is Z. Therefore, the number of all walks of length K plus 1 from I to J is C of Ij, which is equals to the summations of Biz times Azj, summing for all Z in G. It follows from the induction hypothesis that the matrix B defined by Bij is equals to Bij. Capital Bij is equals to small bij fulfills B equals to A to the K. It is immediate from the definition of the adjacency matrix A of G that Aij, capital Aij, is equals to small aij. Therefore, it follows from the definition of a matrix multiplication that C of Ij is equals to the summations of Biz times Azj, summing for all Z in G, is in fact the Ij entry of Ba, which is equals to A to the K plus 1. Indeed, it is the scalar product of the ith row of B and the jth column of A, and our claim is proved. The adjacency matrix of a graph provides a quick way of testing whether the matrix has certain properties. We will discuss testing of a connectivity here. Theorem 10.17. Let G be a simple graph on n vertices, and let A be the adjacency matrix of G. Then G is connected if and only if I plus A to the n minus 1 consists of strictly positive entries. Proof. We know now from exercise 23 of chapter 9 that if there is a walk from I to J in G, then there is a path too. The length of a path in G is at most n minus 1. Therefore, G is connected if and only if, for any pair of distinct vertices I and J, there is a positive integer k which is less than or equals to n minus 1, so that aij to the k is greater than 0, as I plus a to the n minus 1 is equals to the summations of n minus 1 choose k times a to the k, summing with k starting from 0 to n minus 1. The statement follows. If I minus a is invertible, then we have an even simpler way of testing connectivity. Corollary 10.18. Let G be a simple graph on n vertices, let A be the adjacency matrix of G, and assume that I minus A is invertible, then G is connected if and only if I minus A to the inverse consists of strictly positive entries. Proof. Recall that I minus A to the inverse is equals to I plus A squared plus A cubed and so on, and the proof is analogous to that of Theorem 10.17.